teacher or professor at UA.
On the stairs?
Well, no, he got observed in here, and then they were talking on the stairs. But what questions do you have from the homework? That's what we need to focus on.
21.
21? Okay.
1x, that's the same thing as x.
Yeah, 1x is the same thing as x.
Yeah.
So you good?
Yes, sir.
Okay. Any other questions?
Y'all do the one? I did the one. No, I
Yo, I know I saw multiple people get number 11 wrong. Not even close to right. So how are you going to sit there and tell me that you don't have any questions? RJ.
I'm still looking.
How'd you do it?
Oh, so you talking number 11?
Yeah.
Wait, so you didn't know it, but then you're going to sit there and say, oh, no, Mr. Kenny, I don't have any questions? I asked who's got questions, and you're like, which tells me, no, I don't have any questions, I'm good, Mr. Kenny. Like, look, guys, okay, but here's what I need y'all to understand.
I did based on mine.
Homework is not designed to like be a beatdown. It's not supposed to be anything other than, hey, you try these problems at home, 5 of them. So that when you come into class the next day, you can say, hey, Mr. Kenny, I had no clue how to do this. Can you help me out? So we can go over it.
Yeah.
Or, hey, Mr. Kenny, I got it wrong. Can you explain why I got it wrong? Or, hey, Mr. Kenny, I got it right. So I'm good to go. Right? Like, it's supposed to be a check for you to know whether you understand how to do this or not. So you need to do the homework so that you think about mathematics the night before so that you're ready to ask questions when you come in. So number 11 for RJ, perimeter, area, or both? Both, okay. Tony?
I wasn't gonna ask about the complete thing, just about the perimeter.
Just about the perimeter?
Yeah. I see how you got the 2a plus 2b plus 6, but I was wondering.
It's
why-
16.
Oh, it's 16.
Yeah, there's parentheses around this whole thing. That's a 1 and a 6.
Oh, okay, then that completes me.
Yeah, okay.
Wait, so that's 2a plus 2b?
Plus 16.
How you get 16?
Huh?
How did you get 16?
We're going to talk about that in just a second. All right, so is it just number 11 when you ask questions about we're good on 5 and on 6?
Is that, on 5, is that negative 23?
Negative 23x. Which I will point this out. I know I saw some people get numbers 5 and 6 wrong. So what does that mean you should probably be doing right now?
5 and 6.
Uh-huh. If you got 5 or 6 wrong, you should probably do what?
And that's a minus 12?
Before I answer that, if you got 5 or 6 wrong, you should
Gotta ask.
We're gonna ask a question. There we go, right? It's all about questioning. When you question things, you learn. Anybody have a question about 5 or 6?
But just 23x. But the thing is, I can't tell if it's a negative, it's just minus.
Okay. So I will point this out. This is part of the reason why you need to show your work. And I would even, if I were you, if you're getting some of these wrong, I would take the extra step to show the distribution, right? 3x times x plus 3x times 3 minus 4 times 8x plus a negative 4 times 3, right? Show that extra work. Notice 3x times 8x, 24x squared, right? 3x times 3 plus 9x. Negative 4 times 8x is that negative 32x. And then negative 4 times 3, so minus 12. Now, when you look right here in these middle terms, they are like terms, right? We're adding 9x's, we're taking away 32 more x's, so it is supposed to be negative 23x. Does that answer your question?
Well, I understand that part, but what I was asking is why does it become negative 4 times 8x?
Because it was a negative 4 right here.
But at the beginning you said it was a minus.
Okay, so 5 minus 4, right? Isn't that the same thing as 5 plus a negative 4?
Yeah.
So seeing it as a minus 4, you can also see it as a negative 4, and so that's why it became a negative 4 right here, right? Because I'm adding a negative. You can also do it as minus 4 times 3. You can do that. It's just a little wonky when you have a minus and a positive like that. So I added this negative, Or you can just say minus, either one. Does that clarify?
Yeah.
Okay. Alright, any other questions about 5 or 6? We understand what we're doing? Okay? But number 11, okay, so I know this is the beast that got a lot of us, but if you go back to the basics, y'all,
Is that the
legitimately, huh?
This so for the perimeter, that's the only way you can write that?
Nope. There's one other way, we'll talk about it in just a second. But if you go back to the basics, which I'm going to talk, call on what Zay said earlier about area in a second, but when you go back to the basics for perimeter, what do you know about perimeter? What is it really?
What's surrounding the area?
It's what?
Surrounding the area?
It does surround the area, but it's the what around, and it's more about the polygon, right? So the shape, the geometric shape there, right? The area is the inside, the stuff on the inside of the polygon. The perimeter is the something on the outside of the polygon. Starts with a D.
Diameter?
Diameter is part of a circle.
The distance.
There we go. The perimeter is the distance around the polygon, right? Around that shape. Okay? So if I want the distance all the way around here, what am I going to do? Add, right? When I ask y'all to justify, what I'm asking you, you don't have to write this first statement, but if you can just show me the addition, I will be very content with, okay, they actually understand what they're doing. So here's A plus 5 feet. What am I going to add to that next?
B
plus 3 feet.
That's and then
Plus A plus 5 feet. And then B plus 3 feet.
I just wrote like the first one.
Yep.
Yeah, I did times 2.
Oh, well, let's address that. Let's think about it. So, you took your 8 plus 5,
Mm-hmm.
and you just multiply that by 2? What do y'all think? Could we do 2 times 8 plus 5? You say yes. Why, Amity?
Because you're multiplying both sides by 2.
Well, you're multiplying the A plus 5 by 2, but why could we do 2 times A plus 5? There's a little bit...
Because there's 2 sides.
There are 2 sides, and what are we doing with those 2 sides of A plus 5?
Adding.
And how do we show that repeated addition?
Multiplication.
Multiplication, right? You see how there's an A plus 5 there and an A plus 5 there, and we're adding them? So we would, and we're adding 2 of them, so 2 times that A plus 5. Now that's not the whole perimeter though.
Yeah, and then I did plus B. B plus 3 times 2.
And I usually, and it's just traditional to put that coefficient in front. You can definitely, are you putting it at the end here?
Sir?
Are you putting the times 2 at the end?
No, I didn't.
Oh, you put it at the front too?
I just, like, you had already started writing.
Gotcha. So, yeah, 2 times B plus 3. That is one way to write my perimeter. So that would have been completely correct as well. Actually, I'm missing one thing. Feet, right? We've got to have those units in there, right? So how did I get 2A plus 2B plus 16?
Because you added them up. All you did was just add the 2 sides of A plus 5 and the 2 sides of B plus 3 feet.
Okay, so what would A plus 5 plus that A plus 5 be?
That'd be A10, 2A10.
2, not A10, A plus,
A plus 10.
right?
Yeah.
That would be A plus 5 plus A plus 5. And was B plus 3 plus B plus 3?
B plus 6.
Not B plus 6.
2B plus 6.
There we go, 2B plus 6. And so 2A plus 2B plus
16.
16. We good on that perimeter?
Yeah.
Yes, sir.
Now Zay, you did say one thing earlier that I really liked. How did you calculate your area?
Based on time height.
Right. Remember, I even told you yesterday, if you just do area equals base times height, 1, I'd be completely okay with you starting there. Hopefully you get further than that. But so what is the base of this rectangle?
8. I mean, not 8.
No, 8 times 8
Yeah.
plus 5.
A plus 5
I did parentheses, I did,
Hold up, a plus 5 what?
Feet.
Feet.
Oh, yeah,
Yeah.
feet, yeah.
Times
Time.
B plus 3 feet.
Yeah.
And so what did I tell you that you could end with?
A, and B with A, right?
Shit, what we end with.
Yeah, like I don't want you to leave it like this.
Oh,
This is
that's
close.
That's how I left.
Yeah, that's how I left it. I forgot how you said B.
You didn't leave it as a plus 5
Oh.
times b plus 3 and then the units? Because the units need to go together. Because what's feet times feet?
Feet squared.
Feet squared, right?
Oh,
So I at least need you to get to that point.
Okay, now I see.
Does that make sense?
Yes, sir.
We good with that detail? Okay. Now, I will point out, because I've been talking about this with all the classes today, I do want you to start seeing this more and more. An alternate way that I wrote this area was AB plus 3A plus 5B plus 15. Does anyone know or remember or can explain how we got this? Or how it went from here down to here? Based on the conversation we had yesterday. No ideas?
Wait, can you say that again?
How we got from this expression down to this expression, based on what we talked about yesterday? What you got, CJ?
You put it together.
What do you mean?
Like
Hey, let CJ talk first. Don't talk over the man. What are you saying, CJ?
like you solved it.
Now be careful. When we say solve, that means you're looking for a what?
So
Solution. Are we solving this equation to find a solution to the equation?
no.
No. There's another S word you might be able to use here.
Simplify.
Simplify. We could simplify the expression, right? We are doing that. Tony?
I was gonna say simplify.
Yeah, so we are simplifying. Does anyone know how? And I will say, this really doesn't look that much simpler. But there is something I did here to get that. Any ideas? Yeah, I think I pointed this out yesterday to y'all. I don't know. I didn't point it out to any other classes, but did y'all notice that this is 2x plus 6 and this is 2x plus 6? Notice this is 8x plus 3 and this is 8x plus 3?
Yeah.
So the 8x plus 3 has two different things being multiplied by it, right? This 2x plus 6 has two things being multiplied by it. Okay, you see this b plus 3? How many things are over here?
8.
Yeah, how many different terms are right here?
2.
2. Could I take two different things and multiply it by b plus 3?
Yeah.
Notice I'm going to take a and multiply it by b plus 3. Take a and multiply it to both of those. So then b plus 5 times what?
That was, B plus 3.
Anyone know what we would call this, where we take a and multiply by both of those terms and 5 and multiply by both of those terms?
Distributed.
We're just distributing, but it's with a binomial times a binomial. Bi meaning two nomial terms, right? Binomial, two terms, times a binomial, two terms. The whole point of this was to help you start getting prepared for stuff like this. Notice what's a times b? What's a times 3?
3.
What's 5 times b?
5.
5 times 3. That's all it is. It's just distributing. We good on that? Okay, we gotta move quickly now. 20, alright, I did ask you to start thinking on and looking at this one. If I want to find the greatest common factor, what do I need to do first?
Find some factors.
Find some factors, right? 6x squared, how would I factor that? 3 times 2 times x times x. What kind of numbers did RJ factor this into? Primes, right? Where the only factors are 1 in itself. So then how would 18x factor?
3 times
3 times what? Alright, oops, just times x. All right, are we at prime factors now for everything in 18x?
Mm-hmm.
Sure about that?
6.
Yeah, with that 6, can I factor that further?
Yeah.
How do I need to factor that 6 then?
3 times 2.
3 times, yeah.
Notice what's 3 times 3? 9. 9 times 2?
18.
18.
So it's still the same, I'm just factoring it. Now this one's a little tricky with that negative 12. I would take out a negative 1 or factor out a negative 1 first so that I'm dealing with a positive 12, but then how would 12 factor?
4 times
4 times 3? Can anything be factored further there?
4.
4 can be factored into
2 times 2.
2 times 2. Alright, greatest common factor. What common factors do you see?
3.
3, yeah.
They all have a 3?
Yeah.
And 2.
1 3 or multiple 3s?
1.
Just 1, and what else?
1, 2.
1 2. Anything else?
That's it. That's it.
That's it? Not an X?
Not next.
So the GCF is 6. Okay. So we're going to look at our objectives and wrap up 6.2. I do not think we'll get to combining linear functions because I didn't in any previous classes. Please note the big things. We already have constructed tabular, graphical, and algebraic representations. We're going to finish this up a little bit, but the focus today is comparing linear and quadratic functions, right? We want to see how are quadratics, how are linear different in their different representations and in their rates of change. So, yesterday,
Miss Kane.
thank you. By the way, did some of us forget to put up our cell phones? Let's get those up there before I have to start looking in the book who forgot to do it. Okay, so we got Destiny. Who else are we missing? Zay's up there. Destiny. Brooklyn. CJ, you don't have one with you today? Tony?
I haven't had it for 3 days.
You haven't had it for 3 days.
Yeah, you
Where
didn't
is it?
notice?
No, I don't always notice. Okay, so that was it. Thanks for putting yours up, Destiny. Okay. Where did we stop yesterday with our number 4 here? The developing mathematical models. I think we made a table for sure, right? Yeah? Okay, so while you're getting it out, I'll reconstruct the table we started with.
She said this is so great. It's not. It's great.
Okay, so there's the table we started with, or one of the things we created. I don't believe anyone created a graph, did they? No? Yes, Tony?
But we did get to 4 though.
Say again.
We did get to 4.
Yeah. Because there's one thing I know we didn't get to within number 4, so I'm walking us back through what we did do yesterday. Does that make sense? Okay, so what did we do with this table? Or is this all we had with the table?
No, we had some problems about it.
Yeah, we found out that it was quadratic
Okay, how did we find out that it was quadratic?
because the rate of change.
Because of the rate of change. So what do I need to do to find that rate of change? We don't know what to do to find the rate of change?
No, add. Yeah, add.
Oh, were we multiplying or were we adding?
Add.
What were we adding by?
20. There was 21 there.
We get 24, right?
And then 35.
21.
What'd you say, RJ? 35. I thought you said 25. I was like, bro, that ain't 25.
49.
Guys, if you didn't already have this down, you should probably make sure you have this down. This was pretty fundamental to what we did yesterday. Is that where we stopped?
No.
No, what else did we do?
We did add it. No, we had our time.
We what?
We had we was multiplying by 7.
No,
We're multiplying here by 7?
No.
No.
We'll add about 14.
We did another layer of differences?
Yeah, about 14.
Well,
I see what you're talking about, Trey.
So remember, yeah, we're gonna get to that in a second. So what do we call these two sections right here?
First and second.
First,
Which one's first difference, purple or pink?
Purple.
Purple, right? It's literally the first set of differences we looked at. The pink would be my second differences. So remember the second differences, those were constant additive. So that meant that the first differences were linear, and that is my rate of change. All right, and so then that meant that the way that the blocks were adding up was, or the relationship between the size and the blocks was what? Quadratic. Remember, you have to look at that rate of change to prove that it is a quadratic function. Now, from there, we did have something with a 7. What was that, Trey, that you were referring to earlier?
John, how is it multiplying by 7?
What did we multiply by 7?
Blocks.
Not quite. Tony?
the size.
The size, what do you mean the size?
We would do 1 times 7.
Then we had 1
Was
times.
it just 1 times 7?
We had 1
It's
times
1
7.
times 1 times 7.
It was 1 times 1 times 7.
Yeah.
then it was 7. No.
Then here it was, and then
14.
notice that was for size 1.
Oh.
Then for size 2,
2
2
times
times
7
7
times 7.
7.
and then for size 3.
3 times 7 times 7.
And so we assumed for size
4.
n,
It would be
It'll be n times
n
n times 7.
that's a pretty generalized equation. Now we're going to rewrite that in a second, but so where are we getting this 1 times 1 and this 2 times 2 and this 3 times 3? Tony?
If you notice at the corner of the blocks, there's a 4.
You talking about on the, which size?
Size 2.
Okay, so on this corner?
Yeah. So that's 4. There's 4 in the middle. There's 4 in the corners, in all corners, and in the middle of those corners.
So where are you getting the 7 from?
Like in between the corners.
In between the corners?
Yeah.
So you could also say like top, middle, top, or bottom, middle, things like
Yeah.
that. I'm just trying to get you to fully describe those. So notice, there are 4 in each of these because it is a 2 by 2 for that size 2, right?
Yeah.
Was that a similar thing that we saw in size 3?
Yep.
Right? 3 by 3, 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 3 by 3. Woo! 1 by 1, 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 1 by. Couldn't get that last one. 1 by 1. All right. And every time there were how many of those squares?
7.
7. Right? So I do want to point out, I do want to simplify this expression. By the way, is that going to be recursive or explicit? How do you know it's explicit?
Because, because at the end, what we had, I remember when we got to the end, like, this right here,
Yeah. So at the end we got
the 8.
y equals 7n squared.
Yeah.
So why would this be explicit?
Because the exponent, and it's multiplying.
Part of it is the exponent, and multiplying not necessarily. I like what Tony's doing. He's got the right idea over there.
Point slope.
Not point slope. I mean, that's definitely not y equals mx plus b. There might be some information over there. Hey, by the way, Mr. Lipman, can you go get the key for this and take it down?
No,
Oh, you already got
I
that?
was gonna do it when I started working.
Perfect.
Y equals A times B x.
That's raised to the x. You're skipping the definition of what makes an explicit model explicit.
Oh, they have relative inputs and outputs.
Well, relates inputs to outputs, right? Do I have input and do I have an output?
Yeah.
Yes.
Yeah. Also remember for a recursive, how does a recursive always start?
F,
F of n equals,
L times n minus 1.
hold up, not f times n, f of n equals f
And then minus.
of n minus 1. We're not multiplying f times n. Notice how that was f of n? I mean, we substitute n to the f function. That's n minus 1 being substituted into the f function, right? And then what do we do to f of n minus 1? We apply some
Rate of change.
rate of change. Notice, is that my rate of change?
No.
No. It's inputs and outputs. Now, one other thing I want to point out is, does this equation agree with the table that we have a quadratic function?
Yes,
How do you know?
because it's second power.
It's the second power, right? That's an important feature of quadratics that we've discovered is they have a second power. All right, but we did not write a recursive equation, did we?
Nope.
Nope. So what I want to do is I'm going to give you all 7 minutes, right? No more, no less. We need exactly 7. I want you to work within your group. Notice how this first set of differences, that defines my rate of change, correct? Yeah? I want you to figure out a model for that rate of change. One thing I will remind you is that this rate of change is linear. So you might be able to write the equation of a line to help you figure out what that model might be. So don't forget, the rate of change is linear, so we might be able to write the equation of a line to help us there. So let's get to work within your small group, 7 minutes, no more, no less. Say it helps to be awake. It helps to be awake.
So,
Any thoughts? Yeah, what do you know about the linear equation? You both have seen down there the last couple of days. You all okay?
yeah.
You want to talk after class for a minute? You sure? Stuff off a little bit? Okay. You listening? You good? Okay. Hmm? Gotcha. That affects me too when I don't take the lesson I need to. Okay. So you just said it's linear, right? Okay, so what linear equations might you know? Y equals mx plus b. What's the name of that?
I don't think this works.
Open door, please.
Not standard. What does m stand for?
Is that an X on?
Slope and y-intercept, right? So
This one
when you, and don't forget, what we're trying to specifically look at is the rate of change, not at the quadratic, not at the second differences. We're looking at the first differences for that linear rate of change, okay? Do you have a slope and a y-intercept? That's something to think about. I'm going to leave you all to think about that in a second. Are there any other linear equations that we know?
You got it already?
I forgot how to write.
X minus x, 1. There's something we're missing out front.
I know, I'm talking about the.
Do you remember what the additive rate of change is called? Well, repeated addition is shown through multiplication. So what is the additive rate of change called? Well, it's a linear function. Maybe look at your slope-intercept form. What is the additive rate of change called? The slope. Remember, the slope is what you repeatedly add. That's why we multiply this m times all that. Make sense? So yeah, look at your linear rate of change. See if you can maybe use that equation, or that to help you write an equation. What you got?
I was asking for,
Yeah.
so after doing everything, equals everything minus 1, that was the rate of change. What are we supposed
Why'd you do times 14?
Because I was,
Notice that's just a star. That's not multiplication.
yeah,
Because what are you doing with the 14?
I'm just adding it.
You're adding it, right? But also I want to point out, this is your rate of change.
Yeah,
Is that 14?
no.
Remember, you're adding 14 to that rate of change.
I didn't write this down, but, because Broken had said that, because it also had a second set of differences.
It does, yep. And so we do need to use that second set of differences. You're not wrong about that. But here's the thing, and this is what a lot of people forget. Remember what I said before I let y'all get started? But, well, hold on. Are you adding 21 every time? No, right? Remember, we're trying to write something that represents that rate of change, that set of differences. So what I oftentimes do is I like to make a separate table to help me focus on it. Here's my linear rate of change. I add 21, then I add 35, and then I add 49, 63, 77. Notice we're adding 14 to that, but I don't want just that 14, I want this entire rate of change, right? So what's this, and it's linear, so we need the equation of a line. What's an equation of a line I could use? What? Where do you see a 2 and a 5? Just in general, what's an equation of a line I could use? Y'all, what are some equations of a line?
Oh, 6.
You don't see anything up there about equations of a line.
Y mx plus b.
Y equals mx plus b. Or, well, x1 plus y1, right? Because that's the point. So, I mean, we gotta know what our x's are, so we can use this. Any idea what the x is that goes with the 21? That would make a lot of sense, but, and I will say this is why I do this, because I got really thrown off honestly, the first couple of months that I tried writing these equations. But you notice how that 21 is actually getting us to the second term? So it's actually a 2 with the 21. And then a 3. Okay? So I want you to think about what is my slope, what is my x1, what is my
I don't know that
y1
wrong. I don't know it's right.
before we get started, okay?
I don't know it's right.
Alright, what y'all got?
Hmm?
That's not what I asked.
I don't think this is right. I don't know.
Okay, so you got y equals 14.
Cause that's the slope.
That's the slope of the rate of change, right? And then you did x minus 2. And then 4. Where are you getting that from? Now remember, here's our total blocks. Okay, so I understand a little bit about what you're doing, but I want you to think about this. Remember, we're trying to write something for the rate of change. That 14 was for the 21, the 35, the 49, the 63, right? So what is the rate of change when x is 2? How much did we add to get to that x value of 2?
So it's 20.
How much did I add? Does that make sense? All right,
We was close.
you were very close. All right, let's have a quick conversation. So one of the things I want to point out, and this is one of those details that a lot of us are missing. Remember how we're trying to write an expression for this linear rate of change. So focus just on that linear rate of change, right? Can you let Mr. Lipman in? Right? I'm going to focus just on that linear rate of change, and I'm going to make a table to see it more clearly. Right? My linear rate of change, the first thing I'm adding is 21, then 35, then 49, 63, and what was the last one? 77. Because now I can clearly see, hey, the slope for my rate of change is 14. Right? This is linear, so I should be thinking about the equation of a line. And what are some of the major equations of a line? Y equals?
Mx plus b.
Slope and the slope.
And y equals?
M x minus x1 plus y.
Okay. Now, if I use slope-intercept, I need a y-intercept, which means my x needs to be... What does my x need to be if I'm looking at a y-intercept?
0.
0, right?
Yeah.
Well, I don't have any of my x's right now, so we do need to think about this. What is the x value that goes with that 21?
2.
2, right? Notice that 21 is leading me to my second term. That 35 is leading me to my third term.
So,
So do I need to use slope intercept or point slope?
Point slope.
Point slope. So what is my m right here?
14.
14 times x minus
2
2
plus 21.
plus 21. Now you use this point. Could I have used any other point?
Yes, sir.
Yeah, I just used the first point on the table, but yes, I could have used any point there. So, in writing this recursive equation, f of n equals f of n minus 1, and then what?
No, the rate of change.
Yeah, what is my rate of change though?
14.
That it? That's my entire rate of change?
Plus 14.
Plus.
What?
Plus 14.
There is a plus 14, that's my entire rate of change?
You have to have the start point thing.
Guys, what was the point of me writing this equation?
That detail.
This was a
Linear range.
linear rate of change. Is that a line?
Nope.
What was the point of me writing this?
Oh, so can you put that right there?
That's my linear rate of change. Right? So what do I need to put?
That point slope.
So I need to put y plus y equals 14 times x minus 2 plus 21? Is that what needs to go there? We're all looking at it like, I don't know, Mr. Kenny. Is that a fair assessment? You can say that.
We just
But like, here's the thing, I
Yeah,
already
we
have
can.
f of n equals. I don't need another y equals. I just need the expression for the rate of change. Okay? So I just need the expression for the rate of change. There's one other quick issue that we need to address though. What is this input here?
N.
What is this input here?
N. Oh, X.
so
It's x right now, so it needs to be
N.
n. You can either use x all the way through or use n all the way through.
Okay.
Now, Trey, you did pick up something earlier that we still need.
The starting point.
What would be our starting point?
F. No. F. N.
F of 2
No. Wait.
equals 21.
Now, is that f of 2 equals 21, is that for the original quadratic or for the rate of change?
Right.
That's the rate of change.
Yeah.
Remember, this was the rate of change for the quadratic. I need the starting point
For
of the quadratic. Remember, that was recursive for the quadratic.
homework. Yes, go.
Dude, we still have 10 minutes.
We do?
Yes!
God. I thought that was gonna be homework.
Please stop, we gotta get going. So, here's what we need to start at. Y'all need this sheet actually, don't you?
We got it.
I already gave it to you?
No.
Yes, sir.
Yes, sir.
Anyone not have it? Good. Alright, let's go. Alright, so linear functions. So please notice, this is a summary of everything we've learned over the last week and a half. This is a summary of everything that we know about quadratics at this point, and especially how they compare to linear. This is a graphic organizer that you should regularly pay attention to and pull it out during tasks and homework to learn, okay? Linear functions, what do we know about their rate of change? Okay?
Yes, sir.
We need another word with it.
Constant.
It's a constant
Yes, sir.
additive
Oh.
rate of change. The reason I bring it up, over here, with this quadratic, weren't we adding?
Yes.
Yes. It's just we're not constantly adding the same thing. So for a quadratic, what should we say? What kind of rate of change for a quadratic?
Linear rate of change.
It was a linear, but what are we doing? Linear additive, right?
Linear additive.
Right? Quadratics have a linear additive rate of change. How does a linear function look graphically?
Straight line.
Fun fact, do you have to put the word straight in front of line?
No.
No, right? Literally by definition, a line has that slope, that additive rate of change, which forces it to be straight. So it is linear, right? Like a line. Right? Because it could be discrete, so it's not truly a line. But yes, it is linear. What about a quadratic function? What's the graph look like?
The minute.
Purple.
Close. Parabola.
Oh,
That's the name of it, which is what I assumed Tony was going for. But it's
I
called a,
said the A.
yeah, huh?
I said the complete words.
Okay, I didn't, then I misheard it. What does a parabola look like though?
concave up,
Okay, it can be concave up or concave
down.
down, right? So concave up, like a,
Cup.
there we go, concave up like a cup, or concave down,
Round.
like a frown.
You go around.
It's just a little mnemonic device to help us remember it, but concave up and down. Alright, we're going to come back to algebraic because I want to use something from the diagram to help us there. In a linear function, what do we look for in the table?
A linear, I mean, a linear function.
Okay, let's look at a quadratic first then. In a quadratic function, what are we looking for in the table to know that it is quadratic?
Yeah,
We are looking at the rate of change, and what identifies the rate of change?
first and second.
The first and
Second.
second differences, right? For a quadratic, we have both a first set of differences and we have a second set of differences. And in a quadratic, the first differences are what?
You said the first differences or?
The first differences in a quadratic are what?
Linear.
Linear. Right? The first differences were linear. That's what we saw here in purple. That's what makes it quadratic. The second differences are, those are constant additive, right?
Yes, sir.
Okay? So tabularly, for a linear, what are we looking for?
Additive rate of change.
In the what?
In the first
In the
sentence.
first.
So in the first differences, we are looking for constant additive rate of change. Alright, I'm going to erase the rate of change at the top in orange because I want to go back a slide to look at the diagrams. Alright. So I want you to notice, right, logos 1, that was our linear function, right? How did it grow? Like look right here, it got
Longer.
longer. Here in the middle, it got longer, taller, right? It's getting long though in every direction. In the quadratic one, did it just get longer?
You got thicker.
Got thicker or longer and
Wider.
wider, right? You see how it's getting wider there? So, what we would say about the pictorial representation is that this is increasing, it can also decrease, but increases in length,
Increase in length.
right? Notice there's only one dimension. Fun fact, I thought I misspelled dimension last period, and I didn't. I looked at it and I was like, that is a completely wrong word. Okay? But for a quadratic, it's increasing. Huh?
You can get mad at yourself.
Mm-hmm. For a quadratic, it's not just increasing in length, it increases in length and width. I want you to remember, what is length times width, or base times height?
Area.
That's our area. Notice it's increasing in area, or 2 dimensions. Keep in mind, you just said it increases in area, right?
Yes, sir.
And every time we've had units for area, it's been something like feet squared,
Yeah.
or centimeters squared, or inches squared. Hey, what's the power on that unit?
2.
2. And hey, what's the power on a quadratic?
2.
2. You see how those two things are connected?
Yeah.
But if we're talking about increasing in length, we're talking about just miles or meters or yards. What's the power on each of those units? 1, and it's linear, so it's to the first power, right? Last thing we need to look at, we're almost done.
No.
Algebraic representation. In the explicit, what is the highest power?
2.
For a linear function, what is the highest power?
1.
1, right? And when we look at it recursively, and we always have a constant additive rate of change, which remember, you could say it's the common difference, which is what we used to do, but I'm going to call it the slope now, right? It's a constant additive rate of change for a linear function. It's the slope. Okay, but for a quadratic explicitly, what's the highest power?
2.
Yep. Which is why we've always seen y equals x squared, or n squared, there can be more to it. And then recursively, what kind of rate of change does it have? What kind of rate of change does a quadratic have?
Linear.
A linear, right? So we're adding a linear rate of change, which I hope you started to notice we've done a whole lot of point slope with that, right? That's quite often our linear rate of change. So I am ready to go to homework whenever y'all are ready, so you let me know.
You're ready.
All right, here is your homework.
Yeah, no type of announcement, dude.
There it is. No announcements whatsoever. Really quickly, I am passing out old homework that y'all turned in. Every bit of homework that I'm turning in, there's an I and R, and even if there's not, there's an I and R, meaning improve and resubmit. Use the feedback from me and Mr. Lippum so that you can improve what you got. If you did not get anything from me just now, that means you did not turn that homework in. Brooklyn, CJ, Tony, RJ, Trey, Destiny. Those of y'all who did not get homework back from me, that means I did not get homework from you. Yes, sir. You waiting on me or somebody else?
Huh?
You waiting on me or somebody else?
You.
Yeah.
Did you ever?
No, I did not update your grade. Thank you for reminding me.
And you're updating or my dad killed?
Yes, I will get it done tonight.
Thank you.
Yes, sir.
Hey, what up?
That's pretty valid.
Yeah. Valid. Have a great weekend, y'all. Please get these 3 problems done. You'll be proud of RJ. He's actually doing his homework a little bit this week.
Doing your homework, I'm so proud of you. Now I don't have to beat him up.
That's right. We usually don't like our students beaten up. At least I don't.
Well, he should do his homework.
And thank you for helping me get that stuff graded back. That was fun.
That is in fact why they pay me the big bucks.
That's it. Why do you think I want an intern all the time?
Yeah, that's why they pay me the big bucks, man.
Have a good weekend, CJ.
That is what my big paycheck of $0 and 0 salary is all
Yep.
about.